In today's session, we'll be talking about Slurm, Slurm batch scripts, and how to submit jobs to the CHPC cluster. As a quick overview, we'll be talking about what is Slurm and why is it an important skill to know. We'll then discuss how to prepare a job with Slurm and the two main modes that you can interact with Slurm, both batch mode and interactive mode. We'll then go through basic Slurm commands, how to utilize the GPU nodes at the CHPC, and then understanding your job priority scores and your job performance. So starting off with what is Slurm and why is it an important skill to use? So first, to discuss this, let's first do a recap of CHPC resources. The CHPC manages many different clusters, 4 of them being in the general environment and 1 of them being in our protected environment. We also manage virtual machines, storage resources, as well as a variety of other services. Going back to our clusters, these run in condominium mode, which means that the CHPC owns nodes and that they are privately owned nodes that the CHPC manages. With these privately owned nodes, they work in condominium mode, meaning that their owners get priority access to them, but when they're unutilized, people can use them as guests. And so how does Slurm tie into this? Well, Slurm stands for Simple Linux Utility for Resource Management. It's an open source workload manager for clusters. And what this means is that the CHPC can tell Slurm, hey, we have these computational resources and we have users who want to use these for their research. Can you help them be able to submit jobs and manage this in a very hands-off way? Slurm is used by 60% of the top 500 supercomputers, and what I think is kind of a fun fact is it's just developed south of the University of Utah in Lehigh. And so why is Slurm a useful skill to know, and why is it required at the CHPC? Well, let's think about a basic example. So you as a researcher are wanting to use CHPC resources to perform some kind of computational work. Let's say you're wanting to analyze data using an R script. Well, let's look at this simple diagram of an HPC. You begin with you, the researcher, connecting to our clusters. When you first connect to our clusters, you're thrown into a login node. This login node is just meant to manage our users, give them an environment that they can look at and edit files, and submit jobs to get access to compute nodes. These login nodes are not used for computational work. And why is that? Well, let's look at this example. The CHPC has thousands of researchers who at any point in time can be utilizing our systems. If every researcher is connecting to the login node and utilizing it for computational work, you can understand that even within a matter of a few researchers, they could quickly overwhelm the login node, and it would make it to where people couldn't access the CHPC, they couldn't list files, they couldn't even edit files. And so this is where Slurm comes in handy. Slurm allows you, the researcher, to be connected to the CHPC through the login node and then communicate with Slurm to get access to our compute nodes. And so how do you submit a job to Slurm? Well, you first need to ask for the correct resources. And so that's what we're moving on with, is how to ask for these 2 resources through Slurm. And so, like I said, there are 2 main methods to interact with Slurm. There's batch mode and interactive mode. Batch mode is non-interactive, so it's hands-off. This is really great for complete workflows, meaning that if you have a workflow that you know is set and you can just submit it to the cluster and walk away, this is really great. It's very hands-off. The other way is the complete opposite. It's in an interactive mode. And so this works when you need to work with a compute node interactively. So it's very great for debugging or immediate feedback of commands. And so whichever mode you need to work with is really dependent on your workflow and your needs for research. So let's first talk into batch mode and talk about Slurm batch directives. And so here's an example of a batch script. We have bash shell on the left and we have a tcsh shell on the right. So just pay attention to the side that you work with. We're going to start off. I know this looks very overwhelming at first, but we're going to break it down piece by piece. And so let's start off with the batch directives. Anything that begins with #s batch is considered a batch directive. This is what immediately tells Slurm, hey, these are the compute resources that I require, and this is for how long I require them. And so Slurm will be able to read anything that begins with #s batch and assign it to the appropriate resources. And so let's break this down piece by piece. How do we put these batch directives in? So we first begin with the count, partition, and QoS combination, the most important parts here. And so how do you determine what accounts and partitions to use? Well, there are a few different commands. MySNFO and MySQ are a few of those commands, but my favorite is my CHPC batch. Here's an example of my output from my CHPC batch. And when you use this command, the output will be amended to the resources that you have access to. And what I like about the myCHPC batch command is it shows information for every cluster we manage. It even shows you the allocation state, the QoS, account, and partition. And what's nice is it gives you the exact combination of partition, QoS, and account. And so these terms might be unfamiliar to you, so we're going to break them down piece by piece, starting off with allocation states. So there are 4 general allocation states, the first one being the general allocation state. So this means that you can run a job on that partition without any issues. You have equal access to it just like any other user. Then we have the data transfer state, which, as the name suggests, is for data transfer only and not for computational work. So if you're trying to transfer a large amount of data, these data transfer partitions are the ones that you want to target. We have owner nodes. And so this means that you have priority access to these privately owned nodes that the CHPC manages. And if somebody is using these in guest mode, your job has higher priority and will automatically cancel the lower priority guest jobs. And then finally, we have the preemptible section. So you still can run jobs in the partitions in the preemptible section, but they are subject to preemption. Preemption meaning that your job doesn't have as high priority as other jobs there. And if a higher priority job, for instance, someone with access to an owner node, requests access to that same node, their higher priority job will automatically cancel yours. So if you're trying to decide which one to pick, I would suggest sticking to general and owner sections. An account is a Slurm account, and really all it's used for is tracking resource utilization at a user or group level. And so typically these will be named after your research group, but they can have multiple different privileges. And so you might see that naming convention isn't always followed. The most important section here is the partition. A partition refers to a set of nodes with specific resources. And so if you look at partitions named after the cluster, and so for instance, this would be Granite, Kings Peak, Lone Peak, and Notch Peak. These are CHPC owned resources. And the next one would be cluster guest. And so this would be an example of, in the preemptible section, we have Granite guest, Kings Peak guest, Lone Peak guest, and Notch Peak guest. And so these are privately lab owned or PI owned resources that you can utilize in guest mode. And again, these are subject to preemption because they're in the preemptible section. Cluster GPU, as the name suggests, means that these nodes contain GPUs. And so for example, Granite GPU, Kings Peak GPU, Lone Peak GPU, and Notch Peak GPU are those partitions. And then finally, we have owner resources. They are typically named by the PI last name and then the cluster, where CL is the abbreviation for that cluster. And these are in owner mode. You can see that not all owner resources follow this naming convention. By default, all of these partitions are in shared mode, meaning that you can share a node with other jobs. And this is by default to share resources and lower the barrier to getting into a resource. And so now that we've gone through the account, partition, and QoS sections, we're going to go to the next part, which is time. And so --time specifies the wall time in hours, minutes, and seconds. And so in this example, I'm requesting this computational job to run for 2 hours. It's important to note that this 2 hours is a hard limit, meaning that as soon as the job hits 2 hours and 1 second, your job will automatically be canceled if it's still running. So it's good to give yourself a little bit of wiggle room when deciding what time to use. You can also specify this in -t as well. The next one is the number of nodes. and this is dash dash nodes. It can also be specified as dash capital N. And if you are in doubt with the number of nodes to use, always use one. Many programs, or all programs actually, have to be programmed to utilize more than one node. And by default, I would say that more software is typically not programmed well to use multiple nodes. So then you have N tasks. This is the total number of CPUs or cores you want to utilize per node. And dash lowercase n also works for this. You have the amount of memory, and here we also specify the unit of that memory. So here I'm specifying 32 gigabytes of memory to be utilized per node. If you'd like to use the memory of a whole node, you can set memory equal to 0, which sounds counterintuitive, but with Slurm, you're just telling Slurm, hey, I want to utilize all of the memory available in this single node. And then finally, we have the standard output and standard error. This is what would be printed to screen if you were working with the program interactively. And instead of printing to screen, it's being directed into these files, with dash O being the standard output and dash E being the standard error messages. And you can name these whatever you want, but this is what I suggest naming them up here, because the naming convention will be Slurm with your Slurm job ID, and then either .out or .error, and then the node ID. And this is really great for debugging. If your job fails for any reason, I or you can look at this and know exactly what Slurm job it was and what node it ran on. And then finally, we have a couple other options that you can use. There are constraints. Constraints are useful for targeting specific nodes. And so you can target specific nodes by the memory available, by the CPU count, or you can target specific owner nodes. And so in these examples, this constraint is asking for a node with 40 cores. And this constraint is an example of asking for a node with 768 gigabytes of memory. You can also use logicals here. So this is requesting a node with 40 cores and 768 gigabytes of memory, whereas this constraint is asking for a node with either 40 cores or 36 cores. You can also target owner nodes. You might want to do this by looking at the utilization of owner nodes. For instance, if an owner node hasn't been used very frequently in the last 2 weeks, you might want to target that node to lessen your chances of preemption. And so here the same rule applies, where you can specify the owner node, and you can use logicals to say, I want this owner node or this owner node or this one. Another thing I like to use is the Slurm mail features. You can actually have Slurm email you when your job fails, begins, and ends, and all you need to do is provide it your email address and when you want it to email you. This is really great when you need to submit your job to Slurm and then walk away from your computer to perform some kind of wet lab work or whatever else you may need to do. And so now that we have our Slurm batch directives, we're going to go off with the rest of the items that need to be in your Slurm script. And so after the batch directives, you then need to set up your working directory. And here, let's discuss the different locations you have to stage your files for analysis. And so now we're going to move into CHPC storage resources. So the CHPC provides different storage resources. We have home storage, scratch storage, and group space. The home directory space is free. It's automatically provisioned as soon as you get an account, and there's a 50 gigabyte soft limit. The scratch space is also free. It's very useful for intermediate files required during a job. And we have 2 different scratch spaces, VAST and NFS1, the difference only being the software that supports these storage resources. And then finally, we have group space. This is not free. It needs to be purchased by PI. It is purchased by the terabyte. If you're trying to decide which one to use, I would highly recommend using our scratch spaces. The scratch spaces are free to use, and they're very performant with heavy I/O operations. And the reason I mention this is because our home and group spaces are not as performant with heavy I/O operations, meaning that if you're reading and writing tons of files, you have the potential to actually crash these spaces. So I'd recommend taking advantage of the free Scratch space for all of your jobs. And so first, you want to create an environmental variable that points to the Scratch path. And so $user will point to your unit, and $Slurm job ID will point to the Slurm job ID that you're using. And so this is really nice because you can just go ahead and keep this file or keep this line. You never have to change it in any of your Slurm scripts because those environmental variables are dynamic. And then finally, you want to create the working directory. I want to point out here that there are many environmental variables that you can use with Slurm. I showed you Slurm job ID, and Slurm automatically creates these as soon as you submit your script. But there's other environmental variables such as Slurm submit dir, Slurm in nodes, so the number of nodes you request, Slurm in tasks, the number of cores you request. There are many other environmental variables that Slurm automatically utilizes, and if you're curious about those, you can go to this website to look at the different environmental variables that you can utilize in your script. But going back to the Slurm script, so now that we've created the Scratch directory or our working directory, we now want to copy over any of our input files. And so when we copy over these input files, afterwards, we then need to move on over to our Scratch directory. And this change directory to the Scratch directory is very important because we can create it and copy as many files as we want over. But if we never change directories into the Scratch directory, no work is going to be performed there. After you've set up your working directory, you want to load your modules. So for instance, if you're loading or if you're working with an R script, you want to load the R module. Now you want to run the program that you require. And so this would be run exactly as you would from the command line. Finally, the last thing you want to do is to clean up after yourself. So if you are set on your workflow, you might want to copy your output back to your home directory or your group space, move out of your working directory back to home, and then finally clean up the Scratch directory. Now this remove-rf skirter, that can be commented out if you're not positive of your workflow yet, because it automatically will delete all of the files in your working directory. But this is really great if you know what you're putting in this script is going to work. And then you can automatically clean up after yourself. So that's it. We've put together our first Slurm script. Let's call this first Slurm script.sbatch. So now that we've put this together, what do we do with it? How do we give it to Slurm? So now we're going to go into a few basic Slurm commands. Sbatch would be the most important one to know. This is what will actually launch your job and give it to Slurm. So Slurm can read through those sbatch directives, can find the appropriate computational resources to use, and then finally give your job to the correct computational resource, like compute node. And so this is what it looks like when you type sbatch and then the name of your Slurm script. Slurm will first look through all of those sbatch directives, and then as long as everything looks correct, it'll say submitted batch job, and then it will give you a job ID, this numerical sequence. If you want to see where your job is in the queue, you can use the command sq. I highly recommend filtering it using these various techniques because sq by itself will show you all of the jobs currently submitted to the cluster that you're on. So sq-me will just filter for your jobs. Also, you can filter it by unit. So you can do sq-u and then the unit, and that will show only that unit's jobs. If you need to cancel a job, the command is scancel, and you provided the job ID you were given from sbatch. And so here's what that looks like. If I submitted my Slurm script through sbatch, and I got that job ID, but I later found out I made a mistake and I needed to cancel it, all I would say is scancel and then that job ID. Sinfo can give you partition node states, and so this is really helpful if you're trying to see, okay, how many nodes are allocated in this partition? How much memory is available in this partition? If you have questions like this, I highly recommend using the sinfo command. And then finally, we have salloc, and this is useful if you want to start an interactive job, which we're about to get into. And so a quick note, all of these commands only work on the cluster that you are currently logged into. And so a common error I ran into when I was performing work on the CHPC is I would submit my job to Slurm and it would say error. I don't recognize that partition. That partition doesn't exist. And I would look and I'd say that partition does exist. What's going on? And really all it was is I was trying to submit, for instance, to the Kings Peak cluster, but I was currently logged into Notch Peak. So if this is the case for you and you don't want to have to log into the other cluster, all you need to do is amend your sbatch command with the -m flag, which is also equal to -- clusters. So for instance, if I'm on Notch Peak, but I'm trying to submit my job to Kings Peak, I would say sbatch -M Kings Peak and then the name of my Slurm script, and that would solve it. So moving on, now we're going to talk about the other main mode in Slurm, and that is interactive mode. So again, why use an interactive mode? Well, it's really great for getting immediate feedback from your commands, and it's great for debugging. And an interactive command is launched through the salloc command, which we briefly mentioned in the previous slide. And so this works very similarly to batch mode, except you're going to take out the #sbatch from your batch directives. And so here you can see that the same rules apply. You still specify time, the number of cores, the number of nodes, amount of memory, and your account and partition. Except now you'll be submitting it and working interactively on that node instead of walking away from your computer. And what's really nice about this is with salloc, when you submit this command, it will automatically SSH you to the compute node that it assigns you. The use of fastx is really recommended. I find that a lot of times if people want to use interactive mode, it's because they want to interact with GUIs, for instance, RStudio or any other GUIs. And so fastx will automatically enable graphics forwarding, and it also keeps your SSH sessions alive. But if you're also wanting to use GUIs, Open on Demand is another great option for starting that. And so next, let's move on to utilizing GPU nodes. And so there are GPU nodes on all of our clusters. We have a lot of documentation on how to utilize our GPUs on the CHPC website, and we have a variety of different GPUs available. All of our GPU partitions are set up in shared mode, which means that unless you tell Slurm specifically you require a whole node's resources of GPUs, you'll only be getting a sliver of that. And so when you're utilizing GPU nodes, there's only one extra line you have to include, and that's this in batch mode. It is #sbatch -- equals GPU. And all this is telling Slurm is saying, hey, I'm requesting a GPU partition, and in that GPU partition, I need to utilize the GPU. I need you to allocate me the GPU. If you're requesting a GPU in salloc mode, just get rid of this #sbatch and put -- equals GPU. And so this is what you need to put at a minimum. You can also optionally specify the GPU type and the number of GPUs that you require. And so in this example, when we have -- equals GPU, P100, 1, you're requesting one P100 GPU. And so this would be an amended batch job for GPUs where you change the partition, account, and QoS to request the GPU partition. And then you add in this -- flag. And here again, at a minimum, all you need is -- equals GPU, but I've optionally specified requesting one A100 GPU. And so we're going to finish our talk by briefly discussing Slurm job priority scoring metrics and how that relates to how fast your job may start, and finally, how to look at your job performance. So every job that you submit to Slurm, will receive a priority score. And this priority score directly determines how fast your job will start. And so here's an example where I use the SQ command and sorted by priority scores. And so here you can see the first one listed has the highest priority, and it has a node list reason of resources, whereas the rest of them are set to priority. The two differences between the resources and the priority node list reason is resources means that you are next in line. Your job will be starting very soon. As soon as the job before you finishes, your job will start. Priority means that, hey, Slurm is available, or Slurm is aware that your job needs resources and it's working diligently to try and find the correct resources to assign your job. And so by default, everybody gets a base priority. And here you can see that most of these people have a score of 100,000, and then some of them start increasing by a few points. And there are four main factors that will change your base priority score. Again, saying everybody who submits a job starts at getting a base priority score of 100,000. There are four factors. The time in queue is the most important, meaning that if you've spent a lot of time waiting in the Slurm queue, Slurm is going to continually add points to your priority score so that your job receives higher priority to start. Then we have fair share and the number of jobs in the last 2 weeks, which somewhat work together. Fair share meaning that we want everybody to equally access our resources. And so if one person has ran a lot of jobs in the past and then another person hasn't, this other person who hasn't run any jobs will receive a slight bump in their priority score so that they have access to our computational resources as well. And in the same way, Slurm also looks at the number of jobs you've run in the last 2 weeks. And so if you have two users, one who's run 10 jobs in the past 2 weeks and one who's run 0, the person who's run 0 jobs in the last 2 weeks will receive a slight bump in their priority score. And then finally, we have job size. And so this one kind of makes logical sense. If you have someone who has a very, very small number of computational resources that they require versus somebody who's requesting a ton of computational resources, you could see that Slurm would be easier for Slurm to fit in the small job into a compute node than the big job, because the big job requires it to look at more resources that are open and available. And so it's also important to note that only 5 jobs per user will accrue a higher priority score. And so I believe the CHPC has 1,000 job limit that you can submit at one time. So while you can submit 1,000 jobs at a time, only 5 of those jobs will accrue priority and will run. And this is just to ensure that no one person can take over a whole cluster or partition. If you're curious what factors went into giving you in your priority score, you can use the sprio command. You can amend it with the -j flag and give it the job ID. You can even amend it by someone or your own unit. And this will break down exactly what went into deciding your Slurm's priority score. And finally, we have documentation on this as well, if you'd like to read through that. And so the last thing we'll talk about today is checking job performance. And so why would you want to check your job performance? Well, sometimes people request more resources than your job actually needs. And many times when people kind of get into a flow with running jobs, they might want to better tune this so that their jobs are better performant. They're utilizing the resources that they actually ask for. And if you're asking for too many resources, that could increase the amount of time that you're waiting for your job to start. So it might be useful to check your job's performance and try and fine tune the Slurm resources you're asking for. And so when you have an active job, we do allow you the ability to SSH to that node. So again, if you use that SQ command, it will show you exactly what node your job is running on, and then you can actually just directly SSH to that node name. And then there's a few useful commands. My favorite is top. Top will show you the number of cores being utilized, how much memory is being used, the commands actually being run. And so this is helpful to see, okay, how many cores did I request and how many cores are actually being used and what commands are utilizing those cores. PE stat is really nice for looking at an interactive node job, and you can query it. You can also query it without SSHing to it. For instance, if you want to know if something's going on with a node, maybe the node crashed or it's at a drain state, you can use the command scontrol show node and then the node name, and that will show you the status. We also provide a lot of different methods for looking at job stats. For instance, XDMod, or now our new portal website, portal.chpc.utah.edu, will also show exactly how performant your jobs were. The last thing I'll add is back earlier in the slides, I talked about the sinfo command and the sq commands. We do have aliases that give you more information for these commands. And so here's a documentation page where you can grab these, but all you need to do is create a file called .aliases in your home directory, and you can add this info depending on what shell you're in, and then save that file. And you'll finally need to exit your SSH session and re-log in for these changes to take effect. But these commands will show you a lot more information. And so there's a ton of documentation available on Slurm. First off, if you have any questions, you're more than welcome to email the CHPC and ask us questions. We have a lot of documentation here that you can read through. There's also tons of external documentation from Slurm itself. Slurm is a really powerful job workflow manager, and so there's a lot of documentation out there on it. And finally, like I said, if you need help, please contact us. It's our job as user services to make sure that you're getting your research done. So please don't hesitate to contact us. And thank you for learning with us today. Have a good day.